a student is getting ready for a test and he's not able to solve this problem, and he knows that this is the answer, and he wants me to help him find how to solve this problem. So anytime you have a differential equation that the first or second derivative of this equation is to power something, like in this case we have a square, we got to get rid of that term. So in order for us to get rid of that term, we can assume that m is equal to dy over dx. So let's assume that this is m, dy dx is m. So once we assume that, let's go ahead and find the second derivative. So the second derivative of y with respect to x will be the first derivative of m with respect to x. So let's go ahead and write this as dm over dy multiplied by dy over dx. So what we are doing, we are multiplying the top and bottom by dy. And we already have assumed that dy over dx is m, so this term is m. So our second derivative with respect to x is m dm with respect to y. Now that we have the values for the second derivative and the first derivative, let's go ahead and plug it in this formula. So d2y dx2 is that, so multiplied by y, we are going to have y m dm dy plus m squared plus 1 is equal to 0. So now we got rid of this power term and we transferred this equation in this form. Now we can easily solve this differential equation. So let's go ahead and write this equation as, let's write this as ym dm over dy plus 1 plus m squared equal to 0. Now let's multiply both sides of this equation. Let's multiply both sides of this equation by dy divided by y times 1 plus m squared. Now if we multiply the first term, this by the first term, dy's will cancel out, and dy's will cancel out, and y will cancel out. So we are going to have m dm divided by 1 plus m squared. See, if we multiply the first term, we are going to have m dm divided by 1 plus m squared. If we multiply this by the second term, 1 plus m squared will cancel off from the top and bottom, so we are going to have plus dy over y equal to 0. Now let's go ahead and take the integration of both sides. If we look at the integral formulas in a math book, the integration of the first term is 1/2 natural log of 1 plus m squared. And the integration of the second portion is natural log of y is equal to the integration of 0 is a constant, let's say c. Now let's multiply both sides of this equation by 2. So we are going to have natural log of 1 plus m squared plus 2 natural log of y is equal to 2 multiplied by constant, which is another constant. Now here we know that we can write natural log of y, we can write this as 2 natural log of y is the same as natural log of y squared. Is 2 natural log of y, we have a natural log of b is equal to natural log of b to power a. So we use that formula, we are going to have this. And now we also know natural log of a plus b is equal to natural log of a plus natural log of b is equal to natural log of ab. Now we use that formula and we can write this as natural log of 1 plus m squared y squared equal to a constant. So we are using that formula and we write this in this term. Now if the natural log of this term is equal to c, so this term itself is equal to e to power c, and which is again another constant, so this is going to be 1 plus m squared y squared is equal to another constant. And since we have a square here, so let's go ahead and show this constant as a square. The constant, we can show it like a square, doesn't matter. Now here, let's go ahead and simplify this. We are going to have y squared plus m squared y squared is equal to a squared. So m squared y squared is equal to a squared minus y squared. So m squared is equal to a squared minus y squared divided by y squared. So m will be equal to a square root of a squared minus y squared divided by y. Now, in order for us to solve this problem, we assume that the first derivative is equal to m. So now that is the value that we got for m. So let's go ahead and so we know that m is equal to dy over dx, which is now equal to a square root of a squared minus y squared divided by a squared minus y squared divided by y. So now in order for us to solve this first order differential equation, we can again use the separation of variable method. We can write this as we can write this as y dy. We can write that as y dy divided by the square root of a square minus y square y dy, the square root of a square minus y square is equal to dx. Now, in order for us to solve this for y, we need to take integration of both sides of this equation. So here is where you are going to have a hard time unless you have a math handbook. You know, in math handbook, usually there are several hundred integral formulas, and usually I don't think you'll be able to find this formula in just the ordinary book. You got to have a mathematical handbook. And I had the chemical engineering handbook. I look at the integral formulas, and I found the answer for this formula. So the integration for u du over a square root of a square minus u square is equal to a square root of a square minus u square. So using that formula, we can write a square root of a square minus u square is equal to integral of dx. We can write it as x plus a constant. Let's say that constant is b, since we have a b here. So now in here, let's go ahead and here we have y square. So in here, let's go ahead and square both sides of equation. On the left side, we are going to have a square minus y square will be equal to, and then it will be equal to x square plus b square. It is going to be x plus b square. We are squaring both sides of that equation. So now we can write this as x plus b square, and have y goes to the other side of the equation, plus y square will be equal to a square. So this is the general solution for this differential equation. The hardest part to solve a problem like this is really the integration formula. So it is very handy for you to have a math handbook or a chemical engineering handbook or a nuclear engineering handbook. Those handbooks, they have hundreds and hundreds of formulas which can help you. Otherwise, to go ahead and integrate this is going to be a little bit tough. I hope you like it.